bit, and the difference will not come out to be 0.
Yes, sir. Thank you.
Is that clear now?
Yes, sir.
So, first of all, there are particular op amps which have one-sided power supplies. It's rather wrong to say the op amp and op amps behave in one particular way because there are many different kinds. Okay, but the most common ones are the ones we are talking about. Okay, any
Yes,
other
sir.
questions? I hope the sheet is visible to everybody. Okay. If there are no further questions, then I will start talking about an entirely new topic. And that's going to be the last part of our course. There are two things that are left out, that have been left out of the course so far. One of them is oscillators. We just barely touched upon oscillators in the last discussion class, but that was very sketchy and very short. I've made a video on oscillators, which is going to be uploaded soon after a few more edits. I made a couple of mistakes while recording it, so I have to change that. Maybe by tomorrow morning you should have that video. Of course, oscillators are a huge topic, but we are going to touch on just the bare basics, so one video will be enough for that. The other part is digital electronics, which should be at least 1/3, if not half of the course. Not half. Typically, if you look at the course structure, it's 1/4 of the course. But that we have not touched upon at all. So we have only 1 week left. So two or at least at most 3 videos in that, 3 lectures and our discussion class. Well, we will try to cover at least the most important part of that. Now, for that, what I'm going to do is I'm going to assume that everybody here knows some basic digital electronics, in the sense you may not know the circuits involved, but you do know what an AND, or not, NAND, nor are. Is there anybody here who is not aware of what these things are? If so, please say. This is sort of something which people learn in class 11, 12 nowadays. So I think it's safe to assume that most of you at least know parts of this, if not all of this. Just to briefly remind you that in digital electronics, we work with signals which are essentially classifiable as 1 or 0. Now, what exactly is 1 and what exactly is 0? That depends strongly on the particular implementation. It's not always true that 1 is high and 0 is low. There are plenty of implementations where 1 is 0 and 1 is 0 volts and 0 is 5 volts or something like that. But we will, for the sake of definiteness, keep on saying that 1 is high and 0 is low. And typically in most of the implementations, if you have an output which is somewhere between 5 volts and say, okay, I'm making this up because this depends on the details of the implementation. In many implementations, 5 volts to 3.5 volts counts as 1, and 0 to say 2 volts counts as 0. It is not necessarily true that 0 means 0 volts. A small voltage might be 0, but you should realize one thing, that there is a big gap between 2 volts and 3.5 volts. So that's the situation always. It's not as if, say, anything below 2.5 volts is 0 and anything above 2.5 volts is 1. There's always a range in between. And the reason for that is simple. The reason for that is there are situations, because of non-idealities of the circuits involved or other issues, where the voltages change a bit. Okay. But however, if there's a big gap between what you consider to be 1 and what you consider to be 0, the chances of an error being caused because of something which should have been a 1 being read as a 0, because of small fluctuations, does not arise, because there's a big gap in between. Okay. So typically 5 volts will be 1, 4.5 volts will also be 1. But it's very unlikely that a voltage which should have been 5 volts, because of some kind of error in the circuit, some kind of fluctuation in the circuit to be more precise, becomes below 2 volts, and so you read it as a 0. That is unlikely. Now, all of you are aware of this, that nowadays at least most, say, television sets or other devices are, well, make a huge advertisement of being a fully digital circuit and things of that kind, right? And they make it sound as if analog is bad and digital is good. But can anybody tell me why is digital considered to be superior compared to analog? Analog is where voltages are allowed to have continuous values. And digital, for example, the CD, for example, is a digital medium where only certain voltages are allowed, values in between are not. So why would anybody consider analog, digital superior to analog, or the other way around? Say, suppose you're listening to music. The kind of signals that music is made out of are continuous signals, right? Say, when you speak into, or when you sing into a microphone and the microphone converts that to an electrical signal, you get a continuum of signals. You don't suddenly get a bunch of ones and zeros, then ones and zeros. In a digital medium, you convert that first to a bunch of ones and zeros by a process called digitization, and then you store that in a medium or transmit that from one place to another. When you store it in a CD or a DVD, for example. Whereas vinyl, the original records, they were basically analog. Okay, so one answer is depends on how you intend to use and manipulate it. That's a perfectly good answer. Which one is better actually depends very much on what you want to do with it. But when, say, people talk about digital television transmission and say that digital TV is much, much better than analog TV, the kind that used to be used beforehand, earlier. Why is it so much better? Because signals are always continuous. The moment you're digitizing it, you're losing information. Because there you will say that, okay, a particular voltage range, everything in that voltage range is the same value. Everything in the next voltage range is the same value. So it's like converting your marks into grades. That way the smaller details are all lost. So when you're trying to reproduce or send a signal from one place to another, wouldn't you like to have more information in the signal? Losing out on intermediate values, or at least treating all of the intermediate values as the same, may not be a great idea. Does not seem like a great idea. In fact, that is one of the reasons why old timers still say CDs are much better than, CDs are bad and records are much better, because records actually used to record all the signal in almost its entirety. CDs discretize, so you can't record the entire signal. So when somebody says digital television is superior to analog television, they are actually saying that on a specific ground, and the reason is simple. The reason is, if you want to transmit a signal from one place to another, or from one time to another, when you store a signal into a storage medium like a CD, you're storing it today, you'll want to read it tomorrow. So there's a time lag. You want to send a signal from one place to another, you're transmitting it over space. Either way, transmission process, either over space or over time, is error prone. There are situations where fluctuations would occur and there will be errors. Now, in an analog situation, you may have a much richer amount of information in your signal. However, it's very difficult to keep that signal intact and protect it from errors which come in because of small fluctuations. Digital signals, on the other hand, are much more immune to small fluctuations. They're not completely immune, but it's very unlikely that small fluctuations will change your signal drastically. And even if your signal changes by a small amount, there are things called error correcting codes which allow you to actually recover with a very high degree of probability whatever information you originally had. So when you are actually doing something digitally, you are sacrificing some input information, but you're treating your continuous input as a discrete thing. So you're automatically sacrificing some information, but you're not really giving up on all of it. More importantly, when you transmit it over space or over time, chances of errors become a lot less. So your final signal can be transcribed into your output, maybe the image on your television screen, usually much better. So that is why digital is preferred in such situations. But it's important to know that the moment you digitize the signal, you do lose information. So there's a sort of trade-off usually between one or the other. Now, today what I really want to do is, first of all, I wanted to know from all of you, is it okay if I assume everybody knows and or not, NAND, NOR and stuff like that? If not, please speak up. And if nobody says something in 5 seconds, I'm going to assume that everybody knows that, which is fine. So, okay, I think 5 seconds. Yeah, it's 5 seconds now. So everybody knows all of this that have been written down here. And I'm sure all of you also know that you have things called universal gates, that is and or not, for example. If you are given just and or and not gates, you can use them to make up any Boolean circuit or any digital circuit you want. Any circuit which implements a Boolean function, a function whose inputs are zeros and ones and outputs are also a bunch of zeros and ones. But I'm pretty sure you also know, okay, I'm assuming everybody knows this, that NAND alone is universal, so is NOR. In other words, if you have a NAND gate, or not a NAND gate, but a bunch of NAND gates, then you can use it to create all three of these gates and hence any circuit. So I'm pretty sure everybody knows this, but let me just briefly recapitulate how this works. This is the symbol, of course, of the NAND gate, which produces, when you give x and y, the output xy bar, which, by the way, is also x bar or y bar. I hope everybody knows this stuff. Again, if you don't, please let me know. So if you have a NAND gate, how do you produce a NOT out of it? Simple, you just join the two inputs of the NAND gate together, that is, give x to both inputs. So what you get is x bar, and it's one of the standard results of Boolean algebra that x and x is x. So this is x bar, so NOT. So this is how you make a NOT out of it. How do you make an AND? That's simple. You just start with an AND, with a NAND, that is xy. This produces xy bar. Then take its output, feed it to a NOT gate, which you can make out of the NAND gate as we just discussed. And this gives you xy, which is AND. And finally, how do you get an OR? Well, OR, for that, the other version of the NAND is useful. That NAND actually produces x bar plus y bar, shows, that is x bar or y bar, shows that if you gave a NAND gate the inputs x bar and y bar, the output will be x bar's complement plus y bar's complement, which is of course x plus y, x or y. Of course, when I say x plus y, I mean x or y. The question is, how do you get the x bar? Using NAND only. The answer is simple. We know how to produce a NOT gate using NAND only. That's the first thing we learned today, or we talked about a while ago. And so just by making a NAND gate using two NOT gates to give you x bar and y bar, and these NOT gates are also made out of NANDs, so 3 NANDs can give you an OR. So this is something which I am assuming all of you know. You also hopefully also know that the NOR gate is universal in the same sense. This produces x plus y whole bar, which is the same as x bar y bar. And just like NOT, if you were to short the two inputs together and give the same signal to both inputs of a NOR gate, what you will get is x plus x whole bar, and x plus x, x or x is also x in Boolean algebra. So x or x whole bar is x bar. So that's how you get a NOT. Of course, you follow a NOR by a NOT, you get an OR, and you begin a NOR with x bar and y bar. So instead of putting x and y in, if you put in x bar and y bar, of course you're going to get x and y. So if you put two NOT gates made out of NOR gates at the beginning, use them to produce x bar and y bar, and then you feed the result to a NOR gate, you are going to get x and y. So the NOR also can be used to produce NOT and an OR, and hence the NOR alone is also universal. Now, this much I'm pretty sure everybody here knows. But let me just ask you this. Suppose I had a circuit like this. Of course, all of you can figure out what this is doing. This is producing xy. This has y and z both as inputs, so this is producing yz. So what this is producing is xy plus yz, or there are several ways of writing this, x plus z times y and y and so on. So if I gave you a circuit like this and asked you to convert this to a NAND only circuit, how would you proceed? Any ideas? How would you implement the same circuit, one which are made out of AND, OR, and possibly NOT gates as well? This one doesn't have any NOTs, but you can have NOTs. How would you make this into a NAND only circuit? So in principle, you have already learned that any circuit can be implemented using NAND gates only. But suppose I gave you a circuit and asked you to convert it into a NAND only. How would you do that? Any ideas? Is this a new thing? That is this something you already know or you don't? It is one person tell me whether you know it or not, so that I can know that everybody has not gone to sleep.
I guess we know it, but we need to work it out.
You know it, but you need to work it out. That means, okay, everybody knows. One thing you can always do, right? You can just take whatever I wrote on the board on this a while ago. This is how you make an AND, right? So you can replace these two ANDs by pairs of NANDs each. 3 NANDs here, and you're done. So 2 plus 2 plus 3, 7 NAND gates do the job. However, there's a quicker way, and I'm not sure. So since you're saying you have to work it out, I'm pretty sure you don't know the quicker way. The quicker way is actually very simple. The quicker way is to realize that this gate, I hope everybody knows the thing about, right? This is the AND, the circle on top is the complement, so this is not AND, right? XY gives you XY bar. By the way, what is this gate? There's an OR, but with 2 bubbles before. That means the 2 inputs are, if the inputs are X and Y, the OR gate is not getting X and Y, it's getting X bar and Y bar. Since there's an OR gate and it gets X bar and Y bar as the inputs, what's producing is this. What gate is this?
It's a NAND gate.
What gate is this? Somebody said XOR. That's wrong. NOR. That's also wrong. NOR is X plus Y whole bar. Yeah, Aniruddha says NAND. This is also a NAND. One of the basic principles of Boolean algebra, complement of X and Y is not X or not Y. In other words, when will X and Y be false? To make X and Y false, all you need is one of them be false, right? You don't need both of them to be false. X and Y is true only when both of the statements are true. So x and y is false. That is x and xy bar is true. Either when x is false or y is false. So x bar or y bar. So this is basically the two different ways of drawing the same circuit component. Both of these are NAND gates. Okay. Now that you know this, things become very simple. This was an OR gate at the end, right? Okay. Of course, this is wrong because you have complemented the input, but two complements cancel each other, right? And that's it. We are done. Okay, so all you do is if the final gate is an OR, complement the inputs and keep on going back, cancelling those complements. And do it properly. Do it, and you are going to end up with a NAND only implementation. This is a NAND, this is a NAND, so is this. Of course, you can, after you do all this, you may want to redraw this in the traditional way, that is, you may want to erase this out and draw a traditional NAND gate here. Okay. So the outputs at this stage will be xy bar, yz bar, and this will be xy bar, yz bar, whole bar. And there are plenty of different ways of showing that this is the same as this one. Okay. So the basic idea is, if you are given a AND or NOT gate circuit and you want to change it to NAND alone, all you have to do is basically realize that this is a NAND, so is this. Okay. Of course, here what the advantage was, the last gate was an OR gate. So you complemented the input. What if the last gate were an AND gate? Then if you want to change it into a NAND, what you have to do is this. You have to put a complement in the front. But that means you have to put another NOT in front, but you know how to make it NOT using a NAND. That's it. This is really very, very easy. I would urge you to draw whatever AND or NOT gate circuits that you can think of, and try using this technique to convert them to NAND only circuits with minimal effort. Similarly, very, very similarly, this, of course, is a NOR gate, OR followed by a NOT. But so is this. This, of course, when you give x and y, it produces x bar and y bar, which, by the way, is x or y's complement. When is x or y false? Only when both x is false and y is false. Okay, so that's why this works. So these two are the same circuit, and just follow the same procedure. Just use the fact that two complements one after the other cancel each other out. So x bar is x. That's all you really need. It's really rather simple. Okay, so the next topic, and this is the one which I really wanted to do in a live class, because it's very difficult to get the next point across without really getting feedback from you, whether you are following this or not. This is something called a Karnaugh map. Or K-map for short. This is used for simplifying Boolean expressions. But before we go there, I'm assuming people understand what Boolean expressions, etc. are. So, assuming that we have a particular physical or not physical, but some situation in mind where there are three inputs A, B, C, and let's say the problem we want to deal with is that this is a situation where we want to determine majority. There are three people voting, and if the majority vote in favor, majority is 1, then you get a 1. So how many possible choices of input are there? If you have three inputs, each which can take 2 values, the answer, of course, is 2 times 2 times 2, right? A, B, C can take 2 values each. So 8 possible inputs. By the way, how many possible Boolean functions can you have with 3 inputs? Any ideas? How many distinct Boolean functions? With n inputs. You can do it for 3, you can do it for n. First for 3, how many? N equals 3, how many functions can you have? To the n plus 1. Why n plus 1? I mean, when you say to the n plus 1, you mean to the n plus 1 added after that, right? Odd number of functions. You mean to the n plus 1?
Yes, sir.
So you mean to the 4, that is 16 for this particular
Yes,
case?
sir. Yes, sir.
Could you argue that? Why should it be to the 4?
So for every possible input, there is a particular map which either goes to 0 or 1. So two possibilities for every input, and each of them is a valid function. So it will be whatever 2 to the power n into 2.
Well, that's where you're wrong. Your argument was right, almost right. So what else? Anybody else with a different answer? I can't see all the chats that are going on. So somebody, okay, you say 4 is of course wrong. Yeah, but you're right. It's 2 to the 8 in this case. It's not 2 to the 2n, Shayan. It's 2 to the 2 to the n. There's way more than any of the previous answers that came up. It's not exponential in n, it's super exponential in. The argument was almost correct. You had 8 possible inputs, but for each input possibility, there are 2 possible outputs. So the number of possible functions is not 2 into 8, it's 2 to the power 8. 2 possibilities for each one of the inputs. In general, there are 2 to the n possible inputs. If you have n inputs, to the n possible input combinations, for each of them, there are 2 possible outputs. So you get 2 to the 2 to the n. That's a pretty large number. Even for 3 inputs, that's actually 2 to the 8, which is quite big. Not 16, square of that. 256 functions possible with three inputs. So enumerating all of them, while a possibility, there are a finite number after all, it still is not really very convenient. So anyway, this is an important piece of information which you have to remember. The number of possible distinct Boolean functions, which includes a trivial functions like all the output is 0 no matter what the input. The output is 1 no matter what the input. All of these are allowed Boolean functions. Total number of distinct Boolean functions possible is 2 raised to the 2 to the n. In this case, 2 to the power 8. Now, I'm pretty sure all of you also know the standard way of enumerating these functions or these inputs. Go this way. This is one of the standard ways, but this is almost universally what is followed. Oops. Yeah.
100.
Oh, 100. I forgot the 100. In fact, I was about to say that the one advantage of using this universal method is that way you will be sure of not forgetting one of the inputs. But as you saw, just now I forgot one of the inputs. But basically that's it. Right? These are the 8 possible combinations, and the reason why this is written this way, I'm pretty sure anybody who knows a bit of binary number system would immediately understand. These are the numbers 0, 1, 2, 3, 4, 5, 6, 7 in binary. And in fact, in advanced courses, when we have to have a nomenclature for this, we often say this is M0, this is M1, this is M2, and so on. This is M7. Okay, for our particular example, the majority wins rule. This, of course, is 0 because 0 is the majority here. 0 is the majority here as well. So it's 0. This is 1. This is 0. This is 1, 1, 1. So I'm not talking of Karnaugh maps right now. All I'm talking about is how would we go about and simplify this Boolean, find the corresponding Boolean expression and find a simplified version. One simple method, which I'm pretty sure all of you know, is just look at the ones here and read them off. When is the output 1? When the output is 1, when A is 0, B and C are 1, that is when A bar is high. A is 0, of course, means A bar is high, and B is high, and C is high, right? This is A bar, B, C. The rule is simple. If it's 0, put a bar. But what you're really saying is A bar, B, C is a term which is high only when A bar is high, that is A is 0, B is high, C is high. So this, of course, will be a function which gives you a 1 only here, everything else will be zeros. This one, of course, will give you a 1 only if A is high, B is low, C is high. That's A bar, sorry, A, B bar, C. This one, A, B, C bar, and the final one, A, B, C. Now, these individually, each of these essentially give you a result which is 1 only when, for one of these rows, 0 is for all else. But what you want is, you want an output which is 1 either when this combination occurs, or when this occurs, or when this occurs, or when this occurs. So translating that English into logic, this is your expression. This is the function of ABC, which will actually give you the majority rule, majority voting rule. However, so this is the function f that we are aiming for. But as you all can, I'm pretty sure most of you know, this is not the simplest possible way in which you can express this. One immediate thing that you can see is if you combine these two terms, what do you get? You get AB and so these are standard rules of Boolean algebra. This is not really multiplication, that's not really addition, but the rules are sort of the same, and that's why the notation is so useful. And C bar plus C is what? Is either C is high or C is low. Of course, that's a statement which is always true, no matter what C is. So this is 1. And AB and 1 is high whenever AB is high, so that's just AB. So one immediate simplification you can see is this. So instead of 4 terms with 3 factors each, you now have 3 terms out of which one of is very simple, just AB. But I'm also sure that most of you know, if not most of you, at least many of you know, that this is not the simplest that you can have, right? What is the simplest version that you can have? Any idea? Is what I've done, is that clear to everybody? If it's not clear, please let me know. First of all, I read off the lines, the ones here, and translated that to a Boolean expression. Then I simplified that using standard rules of Boolean algebra. I'm assuming you know these rules, because this was something you learned long ago. But if you don't remember them, you can always ask. But do you know how to go further and simplify this? This is not the simplest version. Okay, can anybody tell me what this is? If x is a Boolean variable, what is XOR XOR x? Okay, you don't remember most of Boolean algebra, so that's true. So that's a good point. But okay, I'm going to assume that you can read up this part. Okay, x plus x plus x, most are saying is x, and that's true. And you don't even have to know Boolean algebra for that. All you're saying is when is x or x true? And the answer is when x is true. That's it. Or is a statement which is true when either one of the inputs is true. But if you're saying x or x, then it can be true only if x is true. Right, but that is a hint. Remember, this term simplified because you added an ABC to it. What you can actually do, just as well, let me do it in a different color. You start with A bar BC plus AB bar C plus AB C bar. It would be nice if you had 3 ABCs here so that you could have added it to all 3 terms. You have only 1. But unlike ordinary algebra, Boolean algebra has this huge advantage that 1x is the same as 3x's. You can add it to all 3 of them. Of course, if you do that, this term becomes A bar plus A, which is always true, always 1. So this is BC. B plus B bar is 1, so this gives you AC. So this is the simplest possible version of this particular function. Much, much simpler than the what you started with or what you got by just simplifying one term. Now the problem with this approach is here we were lucky. We could recognize that splitting the ABC, single ABC into 3 pieces and adding them together actually to individual pieces actually makes the whole thing simpler, right? However, that may not always be so obvious what to do to make it simplified. And more importantly, even after you have done something, can you simplify it any further? Or, for example, if I went from here to here at least you could see the ABC. Here you have AB, so you can't even see an ABC, right? Any longer. So instead of starting here, where you can see, okay, this ABC simplifies things, so maybe I will add 3 of them, so I will get a simple answer. Here there are no ABCs that are visible in this expression. This expression is the same as this expression. But if you start from this, it may not be so obvious that you can actually use this to simplify this expression further. Okay? So it may not be obvious that this can be simplified any further. The Karnaugh map or the K map is a way of visually doing this, which works fine for up to 4 variables. In fact, you can do it for up to 6 variables as well. It gets more and more clumsy beyond 4 variables. But up to 4 variables is pretty straightforward and rather nice. And it has many other advantages as well. I hope to be able to convince you of that by the time this class ends. So let's see. The Karnaugh map essentially is a graphical way of denoting the same outputs. So what you do is, first of all, if you have 2 variables, 3 variables, there are 8 possible outputs. So you basically first end up drawing a 8 cells diagram. So you have 8 cells in this diagram, okay? And what you do is something like this. You give a block of 4 of them to one variable. So how do you do that? Well, you may say this row stands for A. That means if A is high, the result will go into any one of these 4. Of course, if this row goes to A, you have no choice about this row. This row cannot be either B or C. This has to be A bar, right? Because these are the 4 rows where 4 cells where A is high. The other 4 must be where A is low. Those belong to A bar. They are nothing to do with B or C. So where would you put B? B could be these 4 cells. Okay. The fact that I have given one whole row to A and 2 smaller columns to B, that's just convention. You can do anything you want. But 4 of these go to B. Okay. That means if B is high, then I'm going to put it in any one of these 4 cells. Okay, if this is A and this is B, where can C be? These 2 rows, these 2 columns, what are they now? Whenever B is high, the output is going to sit in any of these 4 cells. So these 4 cells here, they must be cells where B has to be low. So these 4 are B bar. Okay, they are not C. So how do you put in C? Well, basically you put in C here. So these 4 cells belong to C. Okay, so that's your starting point. You essentially ensure that you assign certain cells for each variable. For each, because you are talking of an 8 cell scenario, because you have only 8 possible inputs, and you ensure that there is an overlap between all of them. So now let me just point out what this means. We had A bar BC, right? Where would A bar BC was 1 for our voting case? Where would that A bar BC go? A bar would mean it would be somewhere here. It has to be both B and C. That means it has to be here. So this is A bar BC. Another one would be A B bar C. A means it has to be in the top row. B bar means it has to be one of these 2 columns. C means it has to be this one. What about ABC bar? ABC bar is where? In A, in B. So in A, in B means in the first 2, so somewhere here. C bar means out of C means here. C is these 2, so this is C bar. And finally ABC. This will go where all A, B, which is to a cell which belongs to both all A, B and C, which means here as well as here as well as here, that means here. So this is how you populate a Karnaugh map. Okay. So you first draw a rectangular grid or square grid depending on how many you have. So for n equals 3, you have 8 possible inputs. N equals 4 variable Karnaugh maps would be 16 inputs. That would be a 4 by 4 square. And half of the cells will be given to one variable, the other half to their complement, and you assign them in this way. Now, what is the advantage of doing this? The answer really is that if you have doublets adjacent to each other, or quartets in the form of a rectangle or a square, or an octet, think 8 things, all of them which are 1, then they have a much simpler expression. So here, for example, you can immediately see that you have 2 adjacent ones. Now, what is the expression for this pair? Notice that if you look at this pair together, they are in A, in B. So they are both A and B, but they are both in and out of C, so C doesn't feature. So this is AB. AB actually would be just this. Okay. So the way you think about it simply is this pair belongs to A definitely, because both of them are in A. C does not come into the expression, you just have AB. That's it. So this is AB, fine. But the important thing is you can use overlaps don't count. You can use one cell as many times as you want, as long as it helps you to get bigger and bigger pieces. So what is this? Note that both of these are in B, right? So B features. One is in A, one is out of A. So A doesn't come in. And again, both of these are in C. So this is actually BC. And finally, you have this. using the same cell over and over again is fine. All you have to do is just look at it and recognize that there are ways of making bigger. Instead of looking at them individually as single cells, you can join them together as dyads, quads, octets, and so on. So this is okay, they have to be either a row to count as a quartet. These are four things close to each other, but they're not in one row or a pair of columns, so they don't really count as a quartet. But you can just visualize things and say that, okay, this is a dyad, this is a dyad, this is a dyad, and this dyad is, of course, is in A, because both of them are in A. It's partly in B, partly out of B, so B doesn't feature, but both of them are in C, so that's AC. And this is a simplification, and by looking at this, you can easily figure out that there is nothing further you can do. There's nothing else that makes it simpler. So this is the simplest possibility. So that's how the Karnaugh map works. However, you will need more practice in this. This is hardly enough. And let me just quickly go through one example, which is very useful. Yeah, go ahead.
Sir, when do we know we are done with
when you can't find any further dyads, quads, the more the number of cells you can take together, the simpler the expression. So either 2 cells, 4 cells, 8 cells, or all 16 cells. That's the simplest, right? If you can't produce any bigger piece, then you are done. So here you can see that the only thing you can produce is this dyad, this dyad, this dyad. It's just something you can see in front of your eyes. You can't have anything more here, right? You do have 4 together, but they are not in a standard row of 4 or square of 4. So they don't count. So maybe one more example will be useful, but that will take some time. Okay, let me just give an example of this. All of you know what this is, right? Or what this is? What is this? What is this thing that I'm drawing? Okay, this is a very bad picture of that. But what exactly am I trying to draw? Can anybody guess that?
The way numbers appear digitally.
Yeah, so there's a formal name for this. Anybody knows the formal name for this? This is actually called a 7-segment display. Do you understand why this is called a 7-segment display? There are 7 segments which are named. Okay, there's a formal nomenclature for them. I'm just making up the letters as of now. But these 7 segments, they're either lighted up or off, depending on whether your input is 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And depending on that, you produce that particular segment lights up. It could be a LED, could be something else. Doesn't matter, but that way you produce representations of the numbers. This, of course, has been superseded now with finer matrix displays so that you can get much neater approximations to numbers, but these are still very much in use. Digital clocks, and whenever you want to show digital process, whenever somebody wants to show hacking is in process on a film, for example, you get to see 7-segment displays sticking down somewhere. Or a time bomb always has a 7-segment display for whatever reason. In films at least, not in real life. But the question that could be that, after all, how many numbers are being input here? What are the inputs? The inputs are the digits 0 to 9, right? How many are they? They are 10 in number. But in binary, you cannot, well, if you want to express 10 distinct inputs, you can't really do that. You need at least either 8, If you are using 3 inputs combination, you can have 8 distinct possibilities, the ones we listed a while ago. Or you can have 16 if you use 4 inputs. Since 10 is somewhere in between, for a 7-segment display, you actually use a binary four binary inputs. Okay, so often written in the binary form as D3, D2, D1, D0. These are just the 0th digit, the 0th digit, 1's digit. Okay, these are not digits. These are 0's bit, 1's bit, 2's bit, 3's bit. And for example, if it's 0, 1, 0, 0, you all know this is the number 4. Okay, so there are 16 possibilities. What kind, say, let me just quickly go over and talk about these 16 possibilities and what the output will be for. What are the 16 possibilities? Of course, you can just write them down, numbers one after the other. Six more, but we will not need those 6 more. We will only focus on these. But let's say we are looking at this top segment in the display, the segment which I've called A. When is that high? That is, when will this light up? When this corresponds to the number 0, this corresponds of course to the number 1, this corresponds to the number 2, and so on. So will this be high? If the input is 0, which of course is 0, 0, 0, 0 here, will the segment A light up? These are the 7 segments, just for your visual imagination. When the input is 0, will A light up? Yes or no?
Yes, sir.
Yes. So this will be, if you're looking for A, this is going to be 1. This is going to be, this is the input 1. When the input is 1, A of course does not light up. 1 is these 2 segments, so this is going to be 0. When the input is 2, again A lights up, so this is going to be 1. Input is 3, lights up. Input 4, A doesn't light up. Input 5, lights up again. 6, lights up again. 7, yes. 8, yes. 9, yes. So there are 2 cases where it doesn't light up. 8 other cases where it does. Okay. So the question is, what is the simplest possible Boolean function of these 4 bits, the D3, D2, D1, D0, which will do this job for me? Okay. Now I don't have the time to do this today because we are out of time right now. But this is important and I don't really want to leave it for the last class. So I have a proposal for you. 9 a.m. Monday. Usually I don't take a class on that day. It is not a live class, but I will take a half an hour class at 9 a.m. Hopefully I should be done in half an hour. And in the meantime, those of you who find the Boolean algebra a bit rusty, you may try to take a look at that once again. You will find that the Karnaugh Map technique, which here of course uses a 4x4 square, because there are 16 possible inputs. The Karnaugh Map technique not only makes it possible to simplify this a lot, actually it becomes even more useful here, because here there are 6 input combinations like 1 0 1 0. Will A light up or not when the input is 1 0 1 0? Can anybody tell me that? If I have 1 0 1 0, will A light up, yes or no? Has everybody understood why these are lighting up? These are just the numbers 1 2 3 4 5 6 7 digits, 7 8 and 9, and All I've done to decide whether they will light up or not is just think of what the numbers look like on the 7-segment display. For these 8 of the 10 possibilities, this segment is going to glow. For the other 2, these 2, it's not going to glow. But can anybody tell me what will happen here? Yes or no? What will happen? Will it glow? Yes or no?
But I think it will.
Sorry, it's too low. I can't hear you. Could it be louder?
I think it will light up.
Why do you think it will light up?
Sir, because 10 might correspond to 0 in some kind of by mod.
Okay, but does it really matter? Okay, let me just tell you this. In a 7-segment display, this is an application, right? You're trying to build a 7-segment display. In a 7-segment display, you're forced to use 4 binary inputs because 3 would be too low. 3 can only go up from 0 to 7, right? Only 8 possibilities. This is as high you can go with 3. You can't go to 8 with 3. Since 8 and 9 do exist, you have to live with 4 inputs. But this particular input combination, that's never going to be encountered, right? If a circuit actually is working and you are really encoding your digits using binary, then 1010 should never occur. 1010 does not stand for a digit, right? So would you like to change your answer? 1010, 1011, 1100, all the other 6, they should never occur. So what should your conclusion be? Should the output be high or low? This is just logic. You should try to guess. Should the output, after all, this is a Boolean function, right? A Boolean function produces an output no matter what the input is. So it will also produce an output for 1010. Do you want it to be high or do you want it to be low?
Low.
Should show no output. Actually, well, it may be surprising, but that's not necessarily the case. The answer here is typically written with an X. X does not mean high or low. X means don't care. Okay. What that means is I don't care whether it's going to give you 0 or 1 because either way, I don't. Well, it literally means I don't care. Either way, it's okay with me. As long as my circuit, whatever function I have, gives me these 10 things right, I don't care what it does with the others. Now, why is that a great thing? The great thing is, you might insist that all of them are low. Somebody else might insist that all of them must be high. But it might so happen that by making some of them high and leaving the rest low, you may end up with a much simpler final function. Okay, so don't cares have this advantage that you can actually make them 1 or 0, whichever way you want it. And I will illustrate on Monday 9 a.m. If you are going to use them judiciously, you can actually simplify functions a lot. Okay. So, and this, what should the don't cares be to simplify this? This is almost impossible to deduce just by any other standard Boolean algebra methods. It's way easier. Using the Karnaugh map, you can see in front of your eyes what you want them to be. Do you want them to be 1 or do you want them to be 0? This is what I need to illustrate the next day. I would urge all of you to at least brush up on these basic rules. Y is x plus x, x. Y is x and x bar 0. Or what is y is x plus 0, x. You might say x plus 0 is x is standard mathematics, but it's not. It's, of course, doesn't mean standard math. Y is x plus 1, 1. That, of course, is not standard math. Why these results work, you should brush up on that by Monday. And on Monday, I hope to be able to be done with this within 15-20 minutes. So maybe half an hour at most. Any questions? If half an hour, then can we have it at 9:30? Okay. Is there any objection to that? Somebody might have a class at 10.
Yes, sir, we have a class at 10, but if you take exactly how.
Okay, maybe then let's do one thing. Let's compromise. Let's start at 9:20. So that I should be able to be finished in by 9:50, but if not, I can get 5 more minutes at least. I don't really want to just leave it in the middle. So 9:20. I will send a mail to everybody. We'll start at 9:20 on Monday. So that will of course be our penultimate discussion class. The last class will be on Friday. And hopefully by that time you should have at least the oscillator video and some of the Boolean digital videos. I'm pretty sure, although you have done, most of you may have done and or not, I'm sure you have not done things like multiplexers or counters. Is that okay? Is that fair to assume? Some people may have already studied multiplexers or ring counters or stuff like that on their own. But I'm sure most of you don't know what counters are, what registers are, or how a memory is made. So these are of course pieces which go towards making various digital circuits, including the computer. So if we had one whole semester of digital electronics, we might even be able to say at the end how you make a computer, at least how the computer works internally. But anyway, that would be way too ambitious, but at least we can make a start of learning the pieces which go inside it. Okay, that will be for next week. Okay, bye for today.
So one more logistical query. What will be the marking scheme like?
The marking scheme, well, that depends primarily. Oh, Monday. Wait a minute. Monday. Okay, Monday is fine. Monday, the Senate meeting is at 11. It will have to be vetted by the Senate. But essentially, since it has been decided that the final exam will not be proctored, or at least will not be externally proctored, it's essentially now up to the teacher. So I will finalize this once the Senate meeting is over. I will let you all know. But roughly, let's say 70 to 80% will come from the internals, and that means the assignments and the class tests. 30 to 20 will come from a single exam that will occur, whose schedule will be given. So the end semester will not be 50 marks, will be at most 30 to 20. And the end semester will be a 2-hour exam with essentially 90-minute exam with 30 minutes additional time given. So that will, when will that be? That the schedule will be put up by the academic staff. Once again, I will be able to give a more precise answer to this after the Senate meeting on Monday. But roughly, this is what is going to happen. Any other queries?
So we are going to have one more class.
Yeah, next Wednesday. And the syllabus for that will be op-amps. Everything about op-amps. Okay? Done. Okay, let's call it a day then.